Hiya. Today I'm gonna create Conway's Game of Life using GPU programming. The plan is to create user interface, then program high-level shader using DirectCompute. The next step is to debug and optimize application and to present game board to the screen using texture. So let's start with Windows desktop application using C++ language. User interface will be simple. I just need menu to start game, maybe to play high speed, and to pause game. Also, let's create memory usage. I'd like to see memory usage during application running. Okay, now I'd like to rename file to game. Let's do this with XML editor. So game menu has play submenu, play high speed, pause, memory usage, and exit items. Now let's bind these items to code. Okay, here it is. This is main procedure and function to process these commands. There are some standard commands here. I just add a new one. ID file start. ID file start sets generations per update. Just one generation per update. File high speed, play high speed, set generations per update. to 10. And file pause set generation 0. The game uses generations. Each generation create new game board state using previous game board. And the case for memory usage. I will create game class, and this class will have this method get memory usage, and this method will return a string or text which will be show message box will show the usage memory usage. And now I create this variable, game variable. Let's add it to header file. Also, I need to include game header. And now I create new class named game that will contain all Direct3D stuff, initializations and other things. Class name will be game. Let's create inline class, just header file. This class will be in the namespace game. Namespace has name game too. Okay, now let's create some methods in this class. I will create the first method from menu. For example, I need set generations per update and get memory usage. Also, I need variable which holds current generation number. So current generation number will be incremented, and generations per update will control the speed of game. By default, game is paused. When I need to change speed, I just call this method set generations per update. Get memory usage returns wstring and video memory info. I need to include DGI headers. As well, I need to include standard string. So include string. Framework header is added by default by Visual Studio, and in the end of framework header I added include string. Then I will add other includes and my namespace, but now it's okay, and we can see window. Let's start and see what happens. Okay, some errors. Set generations per update is not public. To make it public, I add public and 2 colons. Okay, I have menu and memory usage working. Help about, just show about dialog with some information. Let's add another menu programmatically. I'd like to add all accelerators that is available in this system. Accelerators, I will add in accelerators in the additional menu, and let's call this menu accelerators. I added method which create accelerator menu and fills it with adapters. To access all adapters in the system, I need to create factory, DXGI factory. Then I need variable or pointer to actual adapter. And then In the loop, I just add all available adapters. First of all, I get main menu, create sub menu, inside the loop I add get in description code. So here I call get description method to get DXGI adapter description structure, and this structure has name of accelerator. Also it has a dedicated video memory. I add flag checked to the first accelerator. It will be used by default. In the end of loop I just add append item to menu, which I created earlier. Adapter release just releases all resources. After this, I need to add created submenu to the main menu. Also, for example, I add CPU parallel library accelerator. It can be used to compare performance of video card and performance of CPU, Central Processing Unit. And in the end of this method, I add code which gets adapter 3 from simple adapter variable. Adapter 3 is needed to get memory usage information. That's it. Now I need to add all DXGI interfaces and methods. To do this, I create special namespace in the framework header, name it G3D. This namespace will have all objects that I need to make calculations and present results to the screen. So first of all, I need to add library, and this library has Direct3D wrappers. This library wraps DirectX interfaces and objects and make programming simpler. So let's include DXGI, DXH. This library can be downloaded from GitHub. I add namespaces from this library and I create file for this library. Name it dx-. This library created by Kenny Kerr. Okay, now I need IDX adapter interface and create factory. IDX GI interface is included in the GI header file. Okay, create factory is the method which also included in the GI namespace here. Okay, now I will add user namespace D3D. This namespace is created here in framework header. Okay, create factory works compointer. Compointer is smart pointer to automatically manage memory. So I don't need to release IDX adapter interface. And the end of this method, it will be released automatically. For this compointer to work, let's add another header. And okay, it works. There are some things remaining. Adapter 3 and adapter title. Let's create these variables. They are private variables. Adapter 3. Adapter 3 is structure. So I will create structure in my D3D namespace. And this structure will extend object from wrapper library dx.h. Also, I use macro from this library. This macro makes the things simpler. I just need to pass name of my structure, name of extended object, and name of DirectX interface. And this macro create all necessary methods and other stuff. Okay, let's try this interface. Here I don't see additional menu because I need to call this method and accelerate it to main menu in the main C++ file. So in the main C++ file I found the place. I think this is right place to call it. Okay, after window creation, I just call this method with handle of this window. And then this window is shown and is updated. Okay, let's try again. Oh, okay, now we see two accelerators, hardware and software. Microsoft Basic Render Driver is emulator, which is slow, but it supports all features and can be used to test and to debug our shader and our game. Okay, I will use the first accelerators by now. Okay, let's implement memory usage, and that will be end of user interface part. In the next part we will create shader using high-level shader language. getMemoryUsage method calls DirectX method query video memory info, which in turn fills our structure, and this structure has current usage variable and budget variable. Also it has available for reservation memory and current reservation. We can add them later. So let's test this method. I click memory usage and get usage 0 and budget, its overall budget, total memory available to us. Okay, now let's create our game shader. This shader will compute next generation based on previous game board state. So I click on the project by the right mouse button and add new item. There are two ways to create shader. One way is to just add new item and name it here. Another method is to use file new file. Then click graphics and use shader. You can add bitmap image. We need bitmap image to initialize starting game board. Also, we need shader to make a computer program for accelerator. Shader file. You can use this template blank HLSL file. Okay. I will use the first method and just add new item with name game shader .hlsl add. Okay, the first line uh, is used to declare our texture buffer. So game board state will be presented by texture, two-dimensional texture that holds pixels. Every pixel has 4 components. For now we just need one of them. And let's use green component of the pixel to present the cell. If the cell has green color, then it is occupied. If the cell is black color, it is empty. Okay, let's create the next variable, and this texture will be read-write access. So I need to create the next game board using previous, and I will write to the next game board. So I add this read and write chars before the next. Okay, now let's add number of threads. Number of threads represents how many threads will be in the one group. For example, let's set 30 threads by width and 15 threads by vertical, by height. Dispatch thread ID will be used to get actual coordinates or actual index of each thread. This is system value, which will be filled by video card. I need just coordinates x and y from this variable. Okay, this is coordinates of current cell. Now I need to enumerate all the neighbors of this cell. For this, I created array of directions. In the standard grid, rectangular grid, there are 8 directions for neighbors. By diagonals, 4 by vertical and horizontal directions, and 4 is diagonals directions. and we need to count total number of neighbors that occupy it. So I go through this directions array, then add a direction, each direction to current coordinate, and compare with 20 255. The 255 is green color and it represents occupation of the cell. If cell occupied, I just increment neighbors variable. And now, using this neighbors variable, we can apply rules of game. And these rules are very simple. If neighbors are less than 2 or more than 3, then cell will be empty in the next generation. If neighbors equals exactly 3, then the cell will be occupied or keep living in the next generation. Otherwise, it remains the same. And finally, we need to add code that saves this current state in the next generation. So I use coordinates of the current cell and our next texture. Then I just create color for this cell or pixel. Let's color them as just green. And that's all. This simple program represents game of life. Now I need to compile this shader. To compile this shader, let's use inbuilt shader compiler, which embedded with Visual Studio. Let's click on this game shader file, properties, HLSL compiler, shader type is compute shader, shader model 5, and let's choose all platforms and configurations. Shader type, compute shader, and shader model 5 will be used in all platforms and all the configurations. Also, I need to output header file variable name. Let's name it game shader, and header file name will be gameshader.h. Okay. Now reboot the project and we will see any errors. Fix any mistakes and rebuild the project. Okay, Visual Studio tells us that game shader header created, so it appears here in the project. Game shader header has instructions, debug information, even numbers of line in the source code. And it has variable game shader which holds byte shader code. This byte code will be used in the next part. We need game shader byte code to create compute shader on video card. Okay, let's create device resources as well as compute shader in our game file and game class. For this, I add new method, create device dependent resources. This method will need window handle. Also, this method requires all device objects. I declare all device objects. For example, device. Device is needed to create resources. Also, I need device context to order commands for the device. To present graphics, I need a swap chain. And graphics will be presented using render target view and back buffer texture. So our game board will be represented by texture. And this texture will be shown in the window. Now I need compute shader variable, initial texture that will be initialized by a file. For this initial texture, I need a view, shader resource view, and also I need texture for this variable next generation. So these declarations need to be represented in the game textures. So I add two textures and two views for them. The first texture represents previous game board, and the next texture will be represented by the output buffer. And these views will be different. The first view will be shader resource view, read to read the texture by shader, and unordered access view to write new state to the texture. Okay, let's add another method, and this method will be clean up resources. When we need to clean up resources, I need to clean up resources when program ends or device will change, when devices change or swap chain is resized. So now I have all declarations, but I need to add these classes and structures to my D3D interface namespace. So let's create these structures. First of all, I add the device child structure. Device child is the base structure for all objects that will be created by device. And this structure has additional method for debugging that we will use later. This method setDebugName has string argument, and it sets private data with debug object name to any text that will pass. Okay. Let's add another structure, device context. The most structures has simple representations. I just named the structure, set the base class and interface direct to the X interface. So let's add all structures that we need. So we need textures, render views, shader views, unordered access views, as well as resources, because texture and buffer is resources in Direct3D inheritance hierarchy. Okay, now I have all structures except one, device. D3D device. This structure will have few methods. In Direct3D device interface creates textures, compute shaders, so I follow these rules and add some methods to create target views, to create buffer, to create shader resource view, and create an ordered access view, create texture. Also I add method to create texture from file, I need to create initial texture from bitmap, which will be initial board game. Also, I need to create compute shader from memory to use our game shader header with game shader variable and bytecode. And if you need to create compute shader from file, which another method, you can use this macro enable D3D compiler, and it adds another method create compute shader from file, which will use D3D library. And this library needs to I need to specify this library in the beginning of this file framework H. Let's add them here. So I included game shader header, and if enable D3D compiler defined, then I add include D3D compiler header as well as include this library D3D compiler. Okay, for now I just disable this compiler and use embedded compiler of Visual Studio, and I think that's all. Yep, that's all I needed to compile to create compute shader from memory as well as texture. Now let's use these methods inside create device dependent resources. Here we need to initialize all these objects, and first of all I will initialize device. First of all I need to create new device, and this device will be hardware. And let's add create device method inside my D3D namespace. This method specifies flags. I need BGRA support for Direct3D work. Also, if configuration is debug, then just create debugging device. And then I call D3D element create device method. You can specify adapter if you have different accelerators in the system. You can specify type of driver and flex. Actual feature level is the level that will be chosen for this device. And let's add another method get buffer from swap chain. So we can get our texture from swap chain and copy our results to this texture. HR function just checks results of this call and make exception as needed. Okay, device is created. Now let's create swap chain for this window handle. We will use this window handle to create swap chain for our window. And to create swap chain, I use DXGI object factory. It has method create swap chain for each windy, which accepts device object, window handle, and swap chain description. I need to specify that our format for picture on the screen will be RGBA. So I use the second component green to represent game board state. Render target output usage and swap effect discard. The next thing is to get back buffer texture from this swap chain. Oh, by the way, you can use another device, not just hardware. If hardware device is failed to create, then we can create emulated device using WARP device. This is basic render driver which emulates all video card features. It runs on the CPU. Okay, when I created device, then just get immediate context to get commands. For example, dispatch compute shader or present results on the screen. Okay, the next thing I need to do after creation of swap chain is getting back buffer. After this, I will create render target view. This render target view needs to be set. Set render targets 1. Now I just need to add viewport. Viewport is the area where our texture back buffer will be presented. Okay, width and height is our game board size. So let's add these variables. before adapter title. Okay, after setting viewports, let's create our textures. The first texture is initial board state, and this texture created from file initialgameboard.bmp. Let's create this initial game board state. So I add a new item, bitmap file, and it has name initial game board bmp. Add. And this bitmap file has dimensions which is similar to full screen window size. So I set width around 1800 and height to 990. Format will be BGR. I don't have too much options for format. Okay. Now let's create and draw all state. Initial game board state will have groups. These groups has ability to create new moving groups. We can call them gun creators or glider guns or another name. So this group will create small group of other cells which will move by diagonal. And I place these groups all around the initial game board state. Okay, save. And now I return to our code. So okay, I create a texture, initial texture. Let's add texture for previous state. Of course, this texture will be initialized by initial game board. To initialize or copy data from initial texture to the buffer, I use a simple method copy resource from context. Copy resource. The first argument is destination. It's our texture to the buffer, previous state. and initial texture is the source. Okay, now let's create output buffer for the next state. Output buffer has bind flags, unordered access, and everything else is the same as the previous texture. Of course, I need to specify format RGBA, which matches with format of backbuffer texture. This is required for copy resource method to work. If formats or sizes are different, then this method fails. Okay, I created output buffer, and let's copy initial texture to it too, so I can see initial game board state on window load. Okay, now it's time to create a game shader. Game shader created by using device create compute from shader, and I will use game shader variable, which is created by Visual Studio, as well as by shader code. Okay, game shader created, and we just set them to pipeline using context. Of course, we need to set shader resources. First of all, it's texture 2D buffer, and we need to set unordered access views. And this is our texture 2D output buffer. Okay, that's it. This is all I need to see initial texture on the screen. So let's use this new method, create devices resources. And I use this method inside render function, which accepts window handle. And inside render, I check if context is not created. If context empty, then I need to create device-dependent resources using window handle. Is context created, then I just clear render target view using midnight blue color, which is declared in DirectX header, which I need to add inside framework header. For example, here. Okay. Clear render target. Then I copy texture to the output buffer to our back buffer and present back buffer to screen. Okay, for swap chain, present. Okay, and that's it. Let's see now the main C++ file. It has the main game loop. Yep, inside main function we have main message loop. Let's modify it a little bit. For example, I'd like to replace get message with pick message. So I change message. I change this loop by the. So pick message. If message is not presented, there is no message, then it's time to render. Let's render. We can restrict rendering by frames. For example, 30 generations per frame and 30 frames per second. If we need to stop calculation, we can use generation. We can use variable that holds current generation number and just break from this loop. Also, I use window title to present information about current generation and population. By now, let's just render initial texture and check that everything works. Okay, there is the error. This error tells us about we need to include DX guide library. So I add this library and try again. Okay, black screen represents black area represents actual rendering area, and this area has different sizes than our initial game board. We need to resize window, and I can resize window very simple. Inside create window function call, I specify width and height of window. So I just add some margins for width and height because window has title bar and borders. Restart again and see initial game board. Okay, this is state that I started with. Okay, now let's implement update function, which will get information about current state too. So inside main game loop, I add information variable and initialize this variable using gameUpdate method. And then I set window title using information. Okay, game update. Let's add void update. It returns W string. Also it has for loop integer I represents a current generation inside update. So it needs to be less than generations per update. And let's increment it. Inside loop, I dispatch our threads. For each pixel, for each cell, will be dispatched one thread. After all threads computes, I need to copy results to my text2D buffer because I need the next generation's result to make calculations again. So I just swap previous and next generations. Because I don't need previous generations already, it can be override by next generation. Okay, for now that's all. Let's return information about current generation and about adapter title that will be used to calculate this population. Okay, it's time to try. You can see the title is updated and it shows current generation. You can see that our window is updated by current generation texture. Game board is updated. Everything works fine. You can change speed. You can pause to see details. You can see memory usage. Well, by the way, 44 megabytes is used. Okay, Game of Life creates different objects. Uh, there are some different objects. One object is cyclic, one object is still life, and other objects are moving just like this. Sometimes generators are destroyed by occasional moving objects. This is gliders that moves around the table game board. Okay, this generator also destroyed. And so on. Okay, now it's time to debug. What tools I have to debug application? First of all, a simple tool is to add debug names for all objects, like here. Debug name is property which I created for in every device child. So in our create device dependent resources method, we can add device debug name for all objects. Let's add debug name for context, device context, for back buffer, render target view, what else? Maybe initial texture, yes. Initial texture view. Of course, previous state. And its view. Okay. Actually, this debug name is used by different debugging tools to show name of the object. These objects take part in device creation, device running, so it's very useful to set debug name that we can orient, we can simplify our debugging. Okay, that's it. All debug names are set. Now we can use built-in Visual Studio tool to debug graphics. It can be called using Debug menu. Let's click Debug, Graphics, Start Graphics Debugging. To successfully use this tool, I need frame. So this tool can capture device state. So you see capture frame button, and let's capture any frame using print screen too. Okay, I pressed print screen button and frame is captured. So let's close application and let's see this frame. I click on the frame and another Visual Studio Graphics Analyzer is created and show me all information about calls. I need dispatch. Dispatch call used to debug this shader. Device context dispatch. Okay, let's click pipeline stages. Pipeline stages window has text fields to set thread group and number of thread to debug compute shader. So let's click Start Debugging Compute Shader with default thread group and thread. This will be first thread, and you see game shader code, and you can step by step debug. You can debug this game shader step by step and see variables, neighbors, and other. Sometimes graphics diagnostic engine fails and cannot build shader trace. So we can use another method for game shader creation. For example, we can use D3D compiler in our framework. Maybe it will work. So I enable macro, enable D3D macro, D3D compiler. This enables method create compute shader from file, not from memory, as we used earlier. Create compute shader from file also compiles, but it compiles shader after program runs. Program starts and we can change shader before program starts and use it after it starts. Okay, let's use this method create compute shader from file. we I will use it instead create compute shader from memory. So let's comment this line and add create compute shader from file. I know file name, it's game shader HLSL and device. By the way, device interface device don't need it. I don't need this interface because our object this object has this interface pointer already. So I just replace device text by this text. Okay, let's try. Okay, I need white chart here. Let's make sure that everything works fine. Okay. And let's start our graphics debugging again. Play, print screen, and click frame. Then I click dispatch and start the compute shader debugging. Okay, I see my code, game shader code. Okay, it fails. Let's close this. Okay, the next thing to try is analyze performance, analyze times and speed of our game shader. Also, we created memory usage submenu, and we can use it to assess our resource consumption. So to see performance and see durations of different steps of our algorithm, for example, initialization, create device resources, rendering and updates, we can add tool Concurency Visualizer. So you can click Analyze Concurrency Visualizer and add SDK to the project. Or you can download Concurency Visualizer from Microsoft site and add it to Visual Studio. After adding SDK to the project, I can use special header for adding markers. This header named CV markers object. And let's create series performance for our markers. Series created, so let's add some flags. And I will add first flag to the render method. So before create device dependent resources, I will create span and name it create device dependent resources. Then I add flag, name it start. After device creation, I add flag end and delete flag span. So we can see I will see how many seconds these create device dependent resources use. Okay, now let's add another flag span before create device render target view. I create span rendering, right flag clear. Let's add another flag. Copy. Present. And okay. This is render function. Let's add another span for updating. In the beginning of update method, I add flag span with name updating. Right flag dispatch all generations, and after this I add after for loop I add right flag end and delete flag span. Okay, that's it. Now let's start. Analyze Concurency Visualizer. Start with current project. Okay, concurrency visualizers rely on symbol resolution. Enable Microsoft symbol servers and local symbol cache. Okay, configure symbols now. Let's enable Microsoft symbol server and set symbol cache directory. Somewhere on the disk. Okay. Now start high speed, then low speed, and exit. After exit, Concurrency Visualizer collects report. Also, it downloads all files and resolves symbols. So the purpose of these graphics is to see actual performance of this game. And we can see that sometimes it uses more logical cores, and after switching it uses less. Okay, let's see threads or cores. Okay, the main thread is used the most. Okay, thread. You can see in the thread window, you can see performance row. This row represents our series named performance, and you can zoom in and see our spans. Now, for example, span create device dependent resources takes 120 milliseconds. Okay, also we can see that updating starts first, but it don't contains any generations, so generations per update is 0. Let's click on flag dispatch all generations, and yes, there was no calculation, so it just takes very small time. The next span is create device resources, because to render game board we need create contacts and devices. So it starts here. By the way, there is some time to create the flag. Okay, and I see flag start. Yep, this is our flag start. Then let's see another flag. Okay, it takes 100, and another flag is end. Then after updating I see rendering span, and the first flag is clear. Then the second flag is copy. Between them very little time. And present. After present there is very long time. Duration 4 milliseconds approximately. And the last flag, there is another cycle. So there is updating and rendering. Rendering took almost 1 millisecond, updating too small. So let's switch to the time when I set generations per second. Okay, you can see the gap between flags and spans. This gap represents my click on the menu. First time I set generations per second to 1, and updating now takes almost 5 milliseconds. Rendering took just 1 millisecond. Okay, updating now less than 1 millisecond, and so on. So using these graphs and spans, you can analyze performance and see how many time every method and span takes to complete. So I can conclude that rendering is the most expensive operations here, but it takes very small time, just around 6, 7 or even less milliseconds. Okay, that's it. Also we can use performance counters to measure performance time. For example, we can add last time variable in the main C++ file. We can subtract now counter from last time counter to see difference, and this time difference can be used to limit our performance or updates per second. For example, 33 milliseconds represents 33 frames per second, and for this I use chrono, so I need to add chrono. Let's add them here before game and last time variable is needed to compute overall time that we used in our calculations. Okay, last time is set, and then it will be used to calculate difference. So let's see what happens. Okay, play. Yep. This is 30 generations per second. Okay, let's measure overall time. For example, I need to measure how much time was taken to reach generation to 25,000 generation. Okay, let's add in here. By the way, after this loop, let's clean up resources too. So here I set last time clock start before the loop. Okay, and then after loop I compute difference between now and clock start variable, and then message box shows this difference in millisecond. Let's start and exit. Okay, now I see duration of our simulation time. This is duration starts when program starts. So this is overall time of program running, not just simulation. Okay, another feature I'd like to add is population. Let's count population inside shader. So the plan is to calculate overall population of current game boards. For this, I will use simple approach and to calculate population, I just add counter and increment this counter. Let's increment this counter using green. If green is 255, then this expression gives me 1. So this is cell. This cell is leaving, and I add it to counter. If green is 0, this expression gives 0, and counter is not incremented. Okay, for counter I need to add another buffer. Let's create buffer which holds just single integer number. Of course it read write buffer, and for this buffer I need to add device resource. So let's add in the game class another resource for counter. Counter out buffer is counter storage. Access view I need access view to connect this buffer to my shader. And let's create another buffer, staging buffer, to copy result to random access memory, which can be read by CPU. So staging buffer uses shared memory to read actual population by CPU. The next thing, I need to add these new buffers and resources inside cleanup resources method, as well as also I will add these resources to my create device dependent resources function just before creating shaders. Okay, byte widths. Byte widths will be 4 because size of int is 4 bytes. So I create buffer description with default usage and other standard things. Then I created buffer, set debug name, created counter buffer view, and created counter staging buffer, which has CPU access flags. CPU can read and write because we need to nullify this counter after reading, yes? Okay, all resources are created. Then I need to set counter out buffer to compute shader. Okay, now in the update method, I need to add actual region and write in to staging buffer. So let's add region for this operation. Okay, what else I need is population. So this variable will have population, and I use this variable for window title. Now I have to fill this variable by actual value. And I just checked that counter is created, generations per update is more than 0, and then I copy our counter to staging buffer, because only staging buffer can be mapped without failure. So I create mapped resource and 0, notify them. Then I call context map with read write flag and read population from acquired pointer. Then I need to divide this population by generations per update, because our counter is nullified after loop. So I need to divide. In the case of when generations per update is 1, just 1, then I don't need to divide. But when I set them 10 or more, or another number than 1, I need to divide it. Okay. By the way, here is average. Yes, average populations in 10 generations. Let's call them average population. Between updates. Okay, so when generations per update is 1, then population is exact. When generations per update more than 1, it's average population between updates. Okay, and after this, I need to nullify population counter to 0 in staging buffer, then unmap. So staging buffer on the video card has this 0, and then copy from staging buffer to my counter buffer. Okay, that's it. So in this part, I created counter for population. In shader, I add interlocked add. Interlocked add is needed to avoid data races because different threads access the same counter on the video card. Okay, and then I just need to read this counter and output it population to information to window title. Okay, let's start and try our new feature. Okay, generation 0, population 0. Let's play. Oh, you can see that our populations is quite good. Almost 20,000 cells alive. Oh, let's speed up. It's interesting. You can experiment. You can experiment and don't copy counter output buffer and don't copy counter staging buffer to counter buffer here. So 0 don't be copied to our counter. So our counter will be incremented forever. Let's see this in practice. Game play. And you can see that population grows indefinitely, infinitely. So this line is important. If I don't nullify this counter here, let's look what it is. What happens now? I think there is, yeah, population grows indefinitely. So we need all this nullified. Okay, that's it. Thank you very much for watching. Today I created user interface, simple user interface for my game, for Game of Life, and then I add all accelerators available to this user interface and menu. Then I create compute shader using GPU to load GPU with all computations and game rules. Then we will use device resources, compile this shader, and create initial game board state. Yes, we can actually draw initial board state in the bitmap and then use it in the game and see results. Then I tried to debug our code. I added debug names. Also, I add performance measurement. I used Concurrency Visualizer to create graphics and to see performance of different parts of code like rendering, updating, and create device resources method. And then I add another feature, population counting. This is simple example of reduction. You can try to implement another reduction algorithm. For example, you can sum all populations here in different shader using different algorithm. For example, you can divide this texture by parts, and every part can calculate total number of living cell and then sum them up. So thank you very much. Bye bye.